just when my lecture had to start, there are some electric engineering works at the department, and unexpectedly it has interfered with the cloud internet connection. So I'm really very sorry. Such problems happen even in this part of the world. I want to thank organizers for this very interesting seminar and workshop, and the speakers, previous speakers. The lectures were really very enriching with a lot of new information. So I'm afraid that my talk will be boring, will contain many technical details, but probably I have foreseen the question of Mark Isakovich, that what has this to do with theoretical physics. So yesterday I have spoken about the long-range electron transport in polypeptide molecules. The question is this transport stable in the presence of the external fields, and in particular of the magnetic fields? Long-range transport, first of all, is one of the crucial metabolic processes in living systems, because it is part of the redox processes, and redox processes accompany photosynthesis, respiration, so this is a basic process. And we know also that magnetic fields are often used in surroundings. Magnetic fields are used in non-invasive therapies. Strong magnetic fields are used for diagnostics, for instance, in tomography. And how this can happen if, in general, biological tissue is non-magnetic. We are not sensitive to magnetic fields. We do not stick to our refrigerators as the souvenir magnets from various countries. In average, yes, we are non-magnetic, but there are some cells which are magnetic, like, for instance, blood cells, which contain the ions of iron, ferrum. Not only the direct interaction is possible, the direct impact of the magnetic field, it can have effect on the electron transport in these redox processes. So I remind you the yesterday picture that in the redox processes, there is so-called charge transport chain. And this chain is located in the inner membrane of the mitochondria. There are a sequence of polypeptides with large magnetic, with large mass, essential part of which are in the parts of which are in the alpha helical conformation, so that there is regular polypeptide structure. And in these large polypeptides, enzymes, there is this long-range transport of the electrons. So, is it sensitive to magnetic field? And what if it is? So, what are the impacts? Let us again take the simplest model. When we alpha helic, we represent as one-dimensional molecular chain, polypeptides bound by the weak hydrogen bonds. We know that the system is described by the Fröhlich type Hamiltonian. There is the polaron type effect, due to which electron polarizes the molecular chain, creates the formation potential, and is self-trapped in this potential and forms a soliton. But now, to study the impact of the magnetic field, we have to generalize our system for the three-dimensional case. And here, theoretical physics gives us advice what to do. we have to introduce, instead of one-dimensional variable, a continuum or discrete three-dimensional variable. Then we have to make the so-called Peier's transformation, substitute electron momentum by the elongated momentum, where bold A is vector potential of magnetic field and is connected by this relation with the magnetic field. And respectively, our wave function has to be also generalized for the three-dimensional case. So we can write it, represent it as wave function which depends on the longitudinal coordinate along the chain and the transverse part of the electron wave function which depends on the transverse variables y and z, which in general case can be considered as continuum variables, independent of we describe a chain in discrete or in continuum representation. So first, I want to tell you about the continuum model. We have to solve equation of motion for the electron wave function psi, which is connected also with the deformation potential, using this equation where Hamiltonian H is written with taking into account this Peier's transformation, so that we have the deformation potential for the electron wave function sigma rho, where sigma is electron lattice coupling, and we have this part for the kinetic part of the electron wave function. We start with the arbitrary magnetic field, but we know that with this arbitrary, so it has components x, y, and z. But we know also that using substitution of the vector potential by adding gradient of the scalar wave function lambda, at the proper choice of this scalar wave function lambda, we can pick up the Landau gauge when magnetic field is oriented along one of the directions in our system. So from the point of view of that Hamiltonian, which I have shown you before, it is convenient to consider separately two cases of the magnetic field orientation. Here is the polypeptide chain, and we consider two orientations when magnetic field is longitudinal, parallel to the chain, and when it is perpendicular to the chain. So let's consider first case, longitudinal. From the form, taking into account now the explicit form of the magnetic field and vector potential, we see from the Hamiltonian that we can represent our wave function in the longitudinal magnetic field as the product of unperturbed soliton wave function along the molecular chain and the transverse part of the wave function in the longitudinal magnetic field, which depends on these variables y and z in the perpendicular direction. Equations of motion can be solved directly. The answer is that the soliton wave function is not changed, and this transfer wave function is product of the function which depends on one variable z and t, and plane wave in the other direction, where this wave function is the wave function of the harmonic oscillator in the magnetic field. So it has this exponential factor and Hermite polynomial of the displaced argument, and this displacement is related, depends on the transverse quasi-momentum and on magnetic field. So that's the dynamics of a soliton in the longitudinal magnetic field. Much more interesting situation is when soliton is in a perpendicular magnetic field. Perpendicular. So the wave function is the product of the modified soliton wave function with account of the magnetic field and plane wave in the transverse direction. So I don't write explicitly plane wave, obviously it is normalized to 1, while this function now satisfies the modified nonlinear Schrödinger equation. I write it down in the dimensionless units. Tau is adimensional time, x is adimensional coordinate along the chain. This is potential for the wave function, which is created by the deformation. So this is self-interaction, cubic nonlinear Schrödinger equation, but with the extra term in the right-hand side. And this extra term is determined by the magnetic field and by the modification of the deformation of the lattice because of the change of the wave function. There is a coefficient epsilon in the right-hand side, and it is written here. So this coefficient turns out it is proportional to the square of the magnetic field, but it is small even in a very strong magnetic fields, like for instance 10 Tesla. I remind you that in tomography the magnetic fields from 1 to 5 Tesla are used. So this coefficient is small. We can apply to our system perturbation theory. I choose the perturbation theory based on the inverse scattering technique developed by Karpman and Maslom to preserve the essential features of the soliton in this model. And according to this theory, the wave function has the wave function of the modified equation has the standard form of the cubic equation wave function, proportional to the hyperbolic second, but parameters like amplitude, width, velocity, phase depend on time, and this dependence is determined by that extra term, and these dependencies are weakly changing in time. So I calculate explicitly this term of the perturbation and solve the equations for the soliton parameters. I skip the technical details and tell you the results. Soliton amplitude and width does not change in the zero and the first order approximation of the perturbation theory with respect to parameter epsilon. While soliton velocity turns out to be an oscillating function of time. V0 is the initial velocity of the soliton in the absence of the magnetic field, and frequency of oscillations is proportional to the magnetic field and inverse proportional to the cyclotron mass of the soliton. And the cyclotron mass of the soliton is square root of the product of mass of a soliton times mass, effective mass in the transverse direction component. I remind you that soliton mass is the free electron mass in the band plus extra term because the soliton is dressed with phonon clouds because it propagates, electron propagates along the chain together with chain deformation. Okay, that's analytical result. But that's perturbation theory. So it's not obvious that this happens, these conclusions are direct in the more strict consideration. Moreover, we know that discrete systems, in discrete systems, there exists the Peirce-Nabarro relief, due to which soliton has its own oscillations of the velocity. So these two types of the oscillations will interfere, and it's not clear if the soliton will be stable at all. So we studied the problem of magnetic field impact on soliton dynamics in the discrete model. I don't write you these long equations. Tell you only briefly that in main part we have studied weaks fields from very weak up to 10 Tesla. Lattices now we considered longer, up to 100 unit cells or even 300 unit cells to see on the bigger scale impact of the magnetic field. And our numerical simulations have shown that soliton profile changes. These changes are weak, but nevertheless there are these changes. And these changes depends on the parameter values, field intensity, boost velocity, and other models. For instance, on this figure, the acceleration of soliton as function of the magnetic field is shown for different boost velocities, initial velocity of the soliton, launching velocity. This figure shows acceleration of the soliton as function of the magnetic field. What is, sorry, no, where I am? Here. This shows the same acceleration of the soliton as function of magnetic field for another set of the parameter values. And we see that the dependencies are different. This figure shows the acceleration of the soliton as function of the magnetic field for different transverse quasi-momentum, and this dependencies is often linear, but definitely not at any values of the transverse quasi-momentum. And on the contrary to the analytical results, numerical simulations show that there is a critical value of the magnetic field at small values of the transverse quasi-momentum when soliton can start to move. And this critical value is practically linear to the inverse value of the quasi-momentum. These peaks are artifacts of calculations because we had to scan a large amount. Another important result of the numerical simulations is that the amplitude of the soliton and width have big dependence on the magnetic field. So in zero magnetic field and at 10 Tesla, soliton has different widths, different amplitude, and there are radiation, which of course we do not see in the zero order approximation of the perturbation theory. We can calculate this as the second order, but is it worse? Maybe not. That situation deals with the case when we have isolated molecular chain. As the initial condition, we form a very good, very nice soliton profile, switch on adiabatic magnetic field, and see its evolution in time. While in real situation, as I told you before in the beginning, there is first of all transport of an electron from the donor molecule tunneling to the chain. So the question of formation of the soliton in the chain also depends on the parameters of the systems, and now the impact of the magnetic field can be different. So we considered also the system of donor molecular chain, including this initial stage when at the initial time moment electron is fully localized on the donor molecule, and follow the evolution of the wave function. So for instance, this figure shows snapshots of the soliton profile at different time moments, smaller, bigger, in the lattice of the 100 unit cells. soliton profile depends on the system parameters, on the magnetic field, on the transverse quasi-momentum. This shows soliton profile in the vicinity of opposite end of the soliton of the molecular chain at different values of the magnetic field, at the fixed value of the transverse quasi-momentum. This shows the profile of the soliton as at fixed magnetic field for different values of the transverse quasi-momentum. This figure shows soliton width standard deviation as function of magnetic field for different quasi-momenta. So we see that soliton profile gets broader. These simulations allow us to conclude that soliton dynamics is stable in the magnetic fields up to 10 Tesla in the broad range of the interval values. But this dynamics attains oscillating character, oscillatory character. And due to these oscillations, soliton radiates sound electromagnetic waves as linear modes. And these emitted waves, of course, can have a biological role, excitation of the side groups. And we know that biological systems are sensitive to the vibrational spectra. This can be important also for the intercellular communication, but these questions go beyond the pure theoretical physical approach. So the conclusion is that such complex effects of external magnetic fields on the dynamics of solitons in polypeptides can affect the charge transport in redox processes. And possibly it can also explain the physical mechanism of the therapeutic effects of the magnetic field. When magnetic field is switched on, solitons in the redox processes, electrons attain this oscillatory character. There is emission of the sound waves, and this either mobilizes and this affects the efficiency of the charge transport. And in its turn, it can have some physiological impacts, but that is again beyond the question. So that conclusions were based on the result of these numerical simulations, and in the end I show this video which shows dynamics of solitons transferred from the donor molecule into the molecular chain consisting of 300 unit cells. We see well-formed profile of the soliton. It is 2 or 3 hump profile changes, so it's not our bell-like well-formed soliton like in continuum model, but it shows the stability and high efficiency of the soliton transport. So I thank very much my co-author Bernard Pieta, who did these numerical simulations. I acknowledge the support from the Fundamental Research Foundation of Ukraine, from Mathematical Department of University of Durham, and Isaac Newton Institute. And thank you very much for your attention. Thank you.
Thank you, Larissa Brizhik. Thank you. And we have some time for questions, please. Questions from Zoom?
Larissa Brizhik, thank you very much for a very interesting presentation. I wanted to specify in numerical simulations what was the length of polypeptide chain.
In some simulations, we had polypeptide chains of 300 units. In some other simulations to study other directions, we considered chains up to 100 unit cells. So that's not question of the technical limitations.
I see. So it's a rather long polypeptide.
Yes, to see the magnetic field. But we see that in this movie, we see that If the polypeptide is shot, for instance, up to 10 unit cells, the Solleton mechanism there is not needed. Standard tunneling can work, and here the results of studies of Elmar Grigorovich Petrov explain these processes. But if polypeptides are longer, 20 unit cells or longer, then the tunneling mechanism does not work. So in this situation, this self-trapping is very important, since because of the self-trapping, there is compensation of nonlinearity, which tends soliton to be electron to be narrow, and dispersion because of the overlap of electron wave functions, which tends to the dispersion of the wave package. So this works on chains which are longer than 15, 20 unit cells.
I see. Thank you. Thank you very much.
I see Andrei Baumgartner wants to ask a question. Please, Andrei.
Yes, thank you, Larissa, for a very interesting presentation. You mentioned the therapeutic effect of magnetic field. Can you tell us more about that? In what context? Is there some experimental evidence for that, or just a speculation?
Yes, thank you very much. Thank you. That is really a very important question. As a physicist, of course, I cannot insist that this particular model really explains the particular details. But so far as I know, this is the only mechanism which can explain these therapies. First of all, we know that magnetic fields therapies are used to treat all kind of joint diseases. And this is combination of the constant magnetic field and oscillating magnetic fields, but usually this is constant magnetic field. When, for instance, the knee is the leg is put into long sleeve with the constant magnetic field. Secondly, once I was at the conference and there was the medical doctor happened to be there present quite accidentally, who is a specialist expert in the diabetic foot disease. Diabetes is often accompanied by this disease, and there was a company which suggested the devices for treatment, which is again combination of the constant magnetic field when the patient is put on the bed with the magnetic mat field, and then some oscillating patterns. And he asked me, he was very skeptical and said that, look, we are not magnetic. How it is possible that it can have result? It can be result of some placebo effect. And I suggested that there is a possibility to explain this, and try to explain this theoretical physics to the medical doctor. So that was in Italy and near Milan. And he decided that at the hospital they do these studies and buy this device. And they have shown that really these devices have shown good results. And some years later, there was even the conference to which they invited me. And it was purely medical conference, magnetic fields, purely medical conference, diabetic foot disease, and there was the section about the magnetic field interest. But I am aware that these are theoretical models which from direct application to therapy are very distant. Of course, if there was a possibility to work in tighter collaboration with experimentalists, that would be more important. Thank you very much for that good question.
Yeah, that's fascinating. I never knew that magnetic field is used to treat patients.
Yeah.
That's the first time.
Thank you, Larissa Sveredina. Thank you, Andrei. And one more small question.
What is everybody?
Thank you very much for your very nice talk as usual. And my question is simple. What is the order of magnitude of the certain velocity with and without magnetic field?
Repeat the question, please.
What is the velocity in meters per second or millimeters per second?
Yeah, thank you.
With
Thank
and
you.
without magnetic field.
Yeah, thank you.
Yes, and
In these systems, the velocity, for instance, velocity of sound in the polypeptides is about 5,000 meters per second. So that's a big velocity. Of course, it is all on nanoscale. Solitons can move, there is no restriction with which velocity they move, but at real parameters, they can move at velocities which are slower than the velocity of the sound. And what is most important is that velocity of electron transport depends on the metabolism of the system. So in old organisms, this is weaker. In younger organisms, this is faster. It can be from very small to very big. Precise value is not known. There is no possibility to measure this in vivo. While in numerical simulations, this is almost a free parameter. But of course, we considered here from very small velocities to velocities like 1/10 or 1/5 of the velocity of sound. But in analytical model and numerical, this is a free parameter. And the soliton then, of course, adds its changes. So there is acceleration of the soliton by the magnetic field because that is electron, plus there are oscillations. So that is how I can answer your question, but that's a good question. Thank you.
Okay, thank you, Larissa Sveredina. And we are